Hi and welcome to another video about the software VENT.iNG, which is designed for the calculation of explosion relief areas according to European and US American standards like EN 14491 or NFPA 68. In this video we are going to do a little example calculation for a dust collector according to the EN 14491 2012, which is the standard for dust explosion venting in Europe. For this, we have a little example here. The dimensions which we are going to use are shown on the right side. So we have a circular around dust collector with a body diameter of 2 meters. The dust collector has a clean air, which is common for dust collectors. The length of the bags, which is an important dimension, is 2 meters. The body height in total is 5 meters. The vent to top is 3 meters. The hopper height is 2 meters, and the hopper diameter is a bit large, but we just take 1 meter for this example here to make it a bit more simple. This dust collector, in theory or in this example, shall aspirate a dust or material which has the following safety characteristics. The Pmax is 9 bar, the KST is 200. Pmax is the maximum explosion pressure, the KST value is the maximum explosion pressure rise of the dust, which has been tested in the 20-liter sphere by a standard laboratory test. The P-rate max is the maximum explosion pressure the explosion shall be allowed to reach. This is the value which will be used in the calculation, and the strength of the dust collector should be larger than the 0.5 bar. According to the European standard, the strength of the vessel should be usually around 1.1 times the P-rate max, and this is given in the EN 14660, I think. The P-stat is 0.1 bar, which is the opening pressure of the explosion relief device. The panel mass, or the mass of the explosion relief device, is 10 kilogram per square meter, which is important for the determination of the efficiency. According to the EN 14797, which is the testing standard for explosion vent panels or relief systems, the determination of the efficiency is done by this standard, by doing certificate testing by a notified body in Europe, and the efficiency shall be in this calculation, or in this example, 90% of in comparison to, let's say, a weightless aluminum foil, which is usually used in the testing in the certification testing. We will not use any vent duct. We will have no solvents. That means there is no hybrid mixture. The hybrid mixture is when you have a dust in combination with solvents or gases. Then there might be a hybrid mixture which needs a certain calculation method or determination of safety characteristics, which we are not going to do here now. For the bags, we also have the number of the bags, the diameter of the bags, bag spacing. This is also important for the calculation later. So we go to the next slide, I just give you an overview about the different equations which are given in the EN 14491 in 2012. These equations are empirical derived equations. That means that there's been a lot of testing in the last decades to derive these equations for calculation of the explosion vent areas. We're going to use these equations, which mainly use all the values I just showed you, the Pmax KST, the strength of the pre-rate max, reduced explosion over pressure, and so on, and the volume of the vessel and so on, which we're going to calculate later on as well. Going to the next slide, just list here the validity of these equations, when you can use them and when not. So we will be in the limits, but feel free to read through these boundary conditions if you like. So first of all, we need to calculate the volume and also the length of a diameter ratio of the dust collector. For this, especially the length of a diameter ratio, there are certain rules which needs to be applied. So first of all, we need to calculate the volume of the cylindrical part, and we will exclude usually the clean air side, because it doesn't take any part in the explosion itself, because usually the explosion only happens on the raw gas side, and usually the separation plate between clean air side and raw gas side should be at least the same strength as the dust collector, so that the explosion cannot hit through the separation plate. And also the bags should withstand or should not allow the explosion or dust to go on the other side, usually. So what we do is we calculate the volume of the cylindrical part, but for the length over diameter calculation, we also only calculate take the length up to the vent panel to determine the effective volume, which is the volume where the flame would travel until it is relieved, basically. The same we will do for the hopper. So we calculate the hopper volume and multiply this by 1/3, which is given in the EN standard. So and this is because it is considered that only because of the dimension or the shape of the conical part of the dust collector, only 1/3 of the hopper usually takes part in the explosion. And that's why the length of diameter ratio can be reduced by using 1/3 of the volume hopper for the calculation for the effective volume of the hopper. So that means that in total effective volume of, in this case, 7.5 cubic meter is used in this calculation. With the effective volume, you can calculate the effective area, which is the effective volume divided by the height, or basically saying the length or the way the flame could travel, which is in this case from the bottom of the conical part until the upper section of the relief panel, which is 2 meter plus if you take the vent to top dimension plus 2 meter, which is in total then 4 meter. But as I said, the conical part is considered a bit different. So it's 1/3 times 2 meter plus 2 meter, which is then in the end in total only 2.67 meter. And the effective area is then 2.8 square meter for the calculation. The effective diameter for the length over diameter calculation is then calculated by the square root of 4 times the effective area divided by P, and this is 1.89 meter as an effective diameter. Then we take this value, the 1.89, the length it's 4 in total, and the effective diameter is 1.41 and is 1.89, and in total we have then a length over diameter ratio of 1.41, which is then the length over diameter ratio we are going to use in the calculation later on. There is also a rule which says that it's the rule in the EN 14491, which basically says that you can deduct the volume of the filter elements from the explosive volume, so from the raw gas side. And there is also a rule which says basically that you can deduct also the enveloping volume from the filter from the raw gas side when the filter bags are basically close enough together, which means if the distance between filter bags has a certain distance to each other, it should be, as far as I remember, 1/3 times the diameter. So when it's less than that, then you can deduct the enveloping volume, which we do here as well. So we have a certain equation for that, which is given on the right side and used in the calculation. And then we get the volume bags envelope in the end, which we'll be deducting from the raw gas side volume, which is the conical part, and the cylindrical part up to the separation plate. Yeah, so we can see that here on the mask of the calculation and what the results are in the end. So the total volume of the conical part and the cylindrical part already minus the enveloping volume of the filter elements is around 11.5 cubic meter. We have the length of a diameter ratio calculated here, and then the different total volumes, like the body is 12 and so on. Yeah, and this is the equation, or these are the equations which I showed before. So we will just use the different equations for the calculation. So we have different equations. We have A, B, and C. B and C are part of A, basically. That's why we need to calculate B and C first. Doing this, we get in the end certain values which we use here, and then the total vent area calculated is 0.72 square meter geometric wise, which we need to install on the dust collector. As I said before, we have a certain efficiency, which is the efficiency of the vent panel in comparison to a nearly mass-free venting device like an aluminum foil, which is usually not used for venting, but the comparison in the EN 14797 the testing standard is referring to that. So let's assume we have a normal vent panel and the notified body did testing, and they said, okay, we saw that the efficiency in comparison to the aluminum foil is around 90%. So that's why we need to increase the calculated vent area, geometric vent area, by the efficiency factor. So, this means that the geometric, so the corrected geometric area wouldn't be 0.72 square meter anymore, it would be 0.8 square meter to account for the loss of 10% efficiency in this case. Yeah, and this is what how it looks in the calculation mask. So if we use all the information we had in the previous slides, we can also use the efficiency in the calculation sheet. We just open, I'll show you this in the original file. We just put in the values, so we probably can just change some numbers so that you can see what kind of changes you will see in the end. So 9,200, no duct, the mass of the vent. The mass of the vent in this case was 10 kilogram per square meter. The efficiency is 90%. I don't know why it's changing it back. Okay. Yeah, and then we do the calculation and we get the 0.8 square meter in the end. So if the efficiency would be, let's say, 100%, it would just go, just ask us if this is only valid for protective systems with 100%. We say, oh yeah, that's okay. We tapped in 100% and we get the original value, which is 0.72 square meter in the end. You can also do 50%, and then the value doubles, of course. And you have seen the equations. So if you change certain values, let's say we change the volume, then of course the value of the vent area value would increase. Same if you do an increase of LMD, then the vent area value would also increase. We just type in here 0.5, then we don't get this question anymore. And if you increase the strength, of course, if the strength or the reduced explosion pressure is higher, then the value would decrease, the vent area value. But as you can see, there is some more information on the right side. So we just go back into the presentation. The values you saw on the right side are the flame length, then also pressure, resulting pressures outside the venting process, and forces, which are given on the dust collector. So the flame length can be easily calculated by these equations, which is 10 times the volume to the power 1/3, which is the flame length of 22.599 meter. These are the boundary conditions where you can use the equation. The flame width is given by 2.8 times the volume to the power 1/3, which is 6.33 meter. So in the NFPA it's a bit different, but we do this in another video. So the maximum external pressures, so you will have certain pressures outside. Pressures are dangerous for people outside. I will show you that later. So you can calculate the external maximum pressure outside the relief area, which is then calculated by the period max, the vent area, and the volume, which is outside 150 millibar, 0.15 bar. And this maximum pressure would happen, you can calculate that at a distance of around 5.65 meter by this equation. And yeah, and you also can, depending on where you stand, usually where you would stand, you would not, of course, not stand outside the venting process because it's super dangerous. You can also calculate the pressure influence depending on where you stand, like in which angle you would stand in front of the venting. Or yeah, in which distance, I'm sorry, in which distance. The angle can also be calculated when you use this equation. So then you have the alpha value, which is the direction towards the vent opening. And of course, if you standing in front of it, then the pressure would be the highest. And if you're standing left to it, then or right to it, then of course the pressure would decrease. Yeah. So what this means, like external pressures, so that you have an idea, there's an overview about the effects of an explosion in the venting software. So you can find this, I think you can find this here somewhere. Oh no, it's here, sorry, external pressures. So you can find these values here. I just copied that into the presentation. So, and this is taken from this website, which is derived by, I think, nuclear explosion testing. But of course, explosion is, let's say it's explosion, so the pressures do the same thing. As you can see, if you have certain overpressures, let's just take what we calculated, around 150 millibar, then you have already damages to houses, windows and doors are blown out and severe damages, and people would be injured by flying glass and debris. So that's what you would see if you have such a pressure. So that's why if you would apply such a dust collector inside a house or like inside a factory, then this would not be allowed. This is also part of the standards. So meaning you would need to use different explosion protection systems like flameless venting or suppression to account this. Or like you can also use a vent duct, which is then directing the explosion to the outside through the wall. Yeah, and just to give you an idea, usually like mostly people are not killed or injured by the explosion itself. It's because of debris flying around and stuff falling down on people inside buildings. That's how people are getting killed or severely injured. And you don't need much pressure because the buildings cannot tolerate so much pressure, basically. Yeah, so and for original equipment manufacturers, so if you are manufacturing dust collectors, let's say, then you also need to take into account that there are certain recoil forces which are caused by the explosion. These recoil forces also can be calculated by using these equations, which is the FR max, the vent area used by, so we use the vent area and the period max to calculate the recoil force, so the maximum recoil force. You can also calculate the duration of the explosion, which is in this case 580 milliseconds, and the impulse which comes from this is then 14.27 kilonewton per second, which is then used in your calculation if you design such a system to design the dust collector so that it will not fall down or will be kicked down by the explosion due to the recoil forces, basically. Yeah, and that's basically it. What I would like to do here is, and will lead to our next video, is that there of course is another option to calculate dust collectors according to the US American standard. In VENT.ing, you have the possibility to do both calculations, so you can copy basically the values also from your previous calculation, which you have done according to the EN standard, to the NFPA 60H standard. And this you can do by calculating the copy values button. So you just click on what you would like to copy, and then it will ask you if you want to override all entries what you have. So the LVD will not be copied, so the two which we changed here will not be copied, because you need to recalculate that, because the calculation is a bit different. You can also copy the geometries. It calculated, or it took the maximum volume, but there is also a difference in the calculation of NFPA to the EN when it comes to the volume, and deducting any back volume from the total explosive volumes. So, but this will be part of the next video. Yeah, and I hope you enjoyed this. If you have any questions, just leave a comment or send us an email. If you're interested in the software and you want to try it out, just give us, send us also a mail, and we'll come back to you. All right, then see you next time. Thank you, and bye-bye.